Hi, welcome to the chemistry lecture series, and I am Dr. Anima Upadhyay. In the electrochemistry part 3, today we will discuss about the Nernst equation. In the previous lectures on the electrochemistry part 1 and part 2, we have discussed about the electrode potential, standard electrode potential, and also the electrochemical cells. We have discussed about the electrolytic cells and the galvanic cells, and also we have learnt about the differences between the two. The major differences between the two is that in the electrolytic cell, it is the electrical energy which gets converted into the chemical energy, whereas in the galvanic cells, it is the chemical energy which gets converted into the electrical energy, and it is because of the spontaneous redox reactions. Therefore, the delta G in the galvanic cells is negative. Also, we have learned that in the electrolytic cells, the electrodes are immersed in the same electrolyte, and there is only one compartment in which the electrodes and electrolyte is kept. Whereas in the galvanic cells, there are separate compartments for anode and cathode, and these are called half cells, and the electrodes are immersed in the solution of their ions. The half cells in the galvanic cells are connected with the help of salt bridge. So salt bridge is an important part of the galvanic cells. Now, after knowing all these things, let us derive the Nernst equation, which is the principle of all the electrochemical cells. So today's lecture will be on the derivation and applications of Nernst equation. Now let us see what is a Nernst equation. We can explain it as the mathematical expression that gives the effect of concentration of reactants and products on the EMF of the cell. We can also explain Nernst equation as a thermodynamic equation where the change in the free energy and cell potential are related to the concentration of metal ions. For the derivation of Nernst equation, let us consider any cell reaction, which is a redox reaction. Therefore, the decrease in the Gibbs free energy represents maximum work done, and it is represented by the equation minus delta G is equal to W max, where work done is the product of number of coulombs and energy available per coulomb. So we can write W is equal to NFE, where N is the number of electrons transferred during the reaction, F is Faraday's constant and is equal to 96,500 coulombs per mole, and E is the cell potential. So from equation 1 and 2 we get minus delta G is equal to NFE, or we can say E is equal to minus delta G by NF. But under the standard conditions, the standard free energy is represented by delta G naught. So we can write delta G naught is equal to minus NFE naught, or E naught is equal to minus delta G naught by NF. Here E naught is the standard reduction potential. Now because we are considering a redox reaction, it is represented by the equation Mn positive that is the cations will accept the electrons coming from the anodic compartment and get reduced to metal at the cathode. The metal ions will accept the electrons and will get reduced at the cathode, I repeat. So, according to the thermodynamics, the reaction quotient Q is related to the change in the free energy and is given by the van 't Hoff isotherm, which is delta G is equal to delta G naught plus RT ln Q. Here, delta G is the Gibbs free energy, delta G naught is the absolute standard free energy change, T is the absolute temperature, R is the gas constant, and Q is the reaction quotient, which is product by reactant. And in the reaction, because we are taking the reduction reaction, so the reactants are the metal ions and the product is the metal which is deposited at the cathode. Therefore, we can write M by Mn positive as the reaction quotient. Now, let us substitute the values of delta G naught and Q in the equation number 7, that is the want of isotherm. We get minus NFE is equal to minus NFE naught plus RT ln M by Mn positive, product by reactant, and let it be equation number 8. Now let us divide this equation number 8 by minus NF on both the sides. We get the equation E is equal to E naught minus RT by NF ln M by Mn positive. Substitute the values of R, T, N, F and Ln. We get E cell is equal to E naught cell minus 0.0591 by N log M by Mn positive. And this equation is called the Nernst equation. Here, N is the number of electrons transferred during the reaction. So, if we are considering a reaction where only one electron is transferred, N will be equal to 1. But if like Daniell cell, where the number of electrons transferred is 2, the N will be equals to 2. So likewise, N will depend upon the number of electrons transferred during the reaction. Now this Nernst equation has several applications. It helps in the calculation of EMF of the cell using the equation E cell is equal to E naught cell minus 0.0591 by N log product by reactant. It is also helpful in determining the single electrode potential, which is using the equation E cell is equal to E naught cell plus 0.0591 by N log Mn positive. Third important application is in the calculation of the equilibrium constant K. So we all know that at equilibrium, the EMF of a cell is 0. Therefore, we can reduce this equation as 0 is equal to E naught cell minus 0.0591 by N log K. Therefore, log K can be calculated as N E naught cell by 0.0591. Now, after understanding the derivation of the Nernst equation and also learning the applications, in the coming lecture, we will discuss about how to determine the single electrode potential using the reference electrodes. So keep watching the lectures. Thank you very much.